So we looked at going down a ramp with Galileo. We looked at free fall. And the last thing we're going to look at is this idea of symmetry. And here's the basic idea. Instead of Galileo going skiing or skydiving, let's say he decides to just play a little baseball. So Galileo goes outside, he takes a ball, and he throws it up. Okay? Nothing fancy. And what do you know about a ball that's tossed upwards? Eventually it will what? It will come back down. Okay? Not that hard to figure out. You don't have to take physics to know that. But you do have to use a little bit of physics to understand what really happens. Okay? To make your life easier, okay, we're going to pick a nice, easy number for the first quote-unquote 6 seconds of free fall. Okay? I'm just going to pick the number to be 30, just because it's a nice, even number. 30 meters per second. Okay? So the question is, what would happen if you throw a ball upwards at 30 meters per second for the first 6 seconds? I'll zoom in a little bit, like that. There we go. That easier to see? Okay? For the first 6 seconds. Now, normally, we talk about gravity on Earth to be negative what in meters per second? 9.8, right? That's what we tried to measure last Friday when we went out to the football stands and chucked stuff off the bleachers there, yeah? But since we're talking about it, let's just round it off to 10, okay? To make it easier to talk about. Technically, when we calculate, we should use 9.8, 9.81 if you want to be down to the hundredths, but 9.8 good enough, okay? But talking about it, let's just round it off to 10. So at time equals 0, there is no average velocity, and there is no displacement. It's right at our 0 level. Okay? We'll call this 0 meters right here from the point of release from your hand there. Okay? So you tell me, after 1 second, if the acceleration due to gravity is negative 10 meters per second every second, let me just get a little ball here, okay, to visualize this. I throw this up. What would happen after 1 second if you throw it up at 30 meters per second and the acceleration due to gravity is negative 10 meters per second every second? The ball would slow down to what? It would slow down to 20. Good job. Okay? Because as the ball leaves your hand, the only force acting on the ball is a pull of gravity, and it will slow down the ball to 20 meters per second. So something like that. We could visualize that. Draw an arrow that's shorter to represent that velocity vector. How about after 2 seconds? It would slow down to what? If the acceleration to gravity is negative 10 meters per second every second, it would simply slow down to 10 meters per second. Good job. That's all acceleration means. It's the rate of change of velocity, right? You will slow down by 10 meters per second every second. How about, let's sketch that in, okay? So we'll draw an arrow a little bit shorter to represent 10 meters per second as the ball is flying upwards, okay? Finally, after 3 seconds, if the acceleration due to gravity is negative 10 meters per second every second, and you're at 10 meters per second, you will slow down to what? A big fat 0. What? Really? 0? Are you nuts? How can it be 0? There we go. What are you smoking? Are you smoking something you shouldn't be smoking? No. Okay? You're just smoking some physics. We're going to fry your brain naturally, right? So what does that mean? If you're at 0, you're actually where? You are at the very top, exactly, at the peak, the apex of the parabolic trajectory, whatever. Okay? So in real life, you actually kind of know this intuitively, okay? Tennis, great example. When's the best time to serve the ball usually? Right when it's at the what? At the peak, because at that point, the tennis ball isn't moving, right? How about basketball? When you jump up and you want to take your jump shot, when's the best time to take your jump shot? Usually at the what? At the very what? At the peak, because at that point, you're at the highest point of your jump. Also, your body's not moving. You're the most stable. Take your shot. Usually, not always, right? Volleyball. Yay. Here we go, right? When's usually the best time to spike the ball? Boom. Well, usually when you set the ball at the peak there, right? But sometimes they do like a quick set, etc. Okay? But intuitively, you kind of know that. Moving on. How about after 4 seconds? What would the velocity be? Negative 10? What? Are you crazy? Negative. Okay? Good job. What does that mean? The ball is on its way what? Down. You are not crazy. Okay? Yes. Negative just means down. Again, is that important? It is, okay? So I noticed on the problem set, sometimes people screwed up their negative signs, and it's annoying. Like you got the answer right, the magnitude right, but the direction wrong, okay? Velocity is a vector. It has both size and direction. It's important. It makes a big difference between going up and down, okay? Got it? How about after 5 seconds? Negative what? 20. That's weird. Why is it going faster? because you are going which way now? Down, right? Gravity is accelerating the ball back down into your hands there, right? Finally, after 6 seconds, it'll speed up to what? Negative 30 meters per second. You see that? Okay? You're like, I don't get this. This is annoying. We're just doing a bunch of silly numbers and weird math. That's because there's a little pattern that'll make your life easier. Okay? That's what we're looking at in terms of this fancy thing called symmetry, which we'll break down for you in a second. Okay? Now, it's one thing to say how long something is in the air for, how fast it's moving at the end of accelerating at the rate of negative 10 meters per second every second. It's another thing to say how fast on average. Okay, we need to find the average velocity. Why? Because that's the only way we can find then the displacement, the delta x. What I'm actually doing is I'm forcing and tricking you into using two of the nifty equations. You just use nifty equation number 1, Vf equals Vi plus At. I don't know if you realize it or not. That's okay. Now we're going to actually use nifty number 2. You're just not realizing it. Delta x is Vf plus Vi over 2. That's your average velocity times the time. Let's just do it, okay? What's the average of 30 and 20 meters per second? We can do this, right? Average of 30 and 20 is simply, what's halfway in between? 25, right? 30 plus 20 is 50, divided by 2 is 25. How about after 2 seconds? What's the average velocity? Here's how you find it. You take the starting speed, 30, and then you add to it the ending speed, 10, and you divide by 2. 30 plus 10 is what? 40 over 2 is 20. How about after 3 seconds? Excuse me. The average velocity would be 15 meters per second. In fact, what's the pattern? 25, 20, 15, 10, what? 5, and 0. You see that? The average of 30 and 0 is 15. 30, negative 10 is 10. 30 and negative 20 is 5. 30, negative 30 is 0. Why do we do that? Here's why, okay? It's another thing to say how long, that's time, how fast at the end of free fall, that's velocity final, how fast on average, but then how far. How far did the ball go? So let's see if you can figure this out. After 1 second, if I throw a ball up at 30 meters per second, it slows down to 20, okay? Does it go 30 meters? Does it go 20? Or does it only go what? Anyone got this here? Are you awake? Tricky, right? How far does the ball go after 1 second? Can you figure it out? It started off at 30. It slowed down to 20. So on average, after 1 second, it was only going how fast? 25 meters per second for 1 second. The ball will only go 25 meters in the air. You see that? So even though we throw the ball up at 30 meters per second, yeah, it doesn't go 30 meters. It doesn't go 20 because it slowed down to 20. On average, it's only going 25 meters per second. Okay? How about after 2 seconds? Does it go 10 meters? Does it go 30 meters? Or does it go 2 times 20? What's 2 times 20, guys? 40. Okay? So in fact, we can find the displacement by taking the time multiplied by the average velocity. So after 3 seconds, how high does the ball go? 45. Okay? After 4 seconds, how high does the ball go? 4 times 10 is 40. You see that? Hey, wait a second. Is 40 deja vu? It is. That's what we got at what? 2 seconds. You see that? How about after 5 seconds? 5 times 5 is what? 25. Hey, that's deja vu also. That's what we got at 1 second. And after 6 seconds, what do you get? What? 0. Are you crazy? Bingo. Where is the ball? It is back where? Back in your hands. Notice there's a pattern here, okay? This is what we call symmetry here. At time equals 0, the ball is at 0 meters. After 1 second, it flies in the air to 25 meters. After 2 seconds, it flies to 40 meters. After 3 seconds, it flies to 45 meters. That's at the peak. And then on the way down, we hit the distances again. We hit 40 meters, 25 meters, and then finally after 6 seconds, we're back where we started. Okay? So in math, okay, in geometry, whatever you want to call it, there's this thing called symmetry. S-Y-M-M-E-T-R-Y. Big fancy word, okay? Symmetry here. The human body is symmetrical. If you take a mirror and you put it up to your face, okay, you ever try this before? And then you hold it sideways up to your face, okay, and then you look at yourself there, right? The left side of your body should match the right side of your body there, yeah? In terms of symmetry, you should have balance there. I think a while ago, Time Magazine had a cover article looking at science of what makes people good looking. Woo, okay? And I think they featured Denzel Washington. There we go. Fine looking guy there, yeah? Because Denzel's face is perfectly symmetrical. They actually took his face, chopped it in half, and then they mirrored it on the computer there, and he looks the same. And then I think they picked on, what was it, like one of Julia Roberts' ex-husband, I forgot which one. I think he's a country singer dude, how his face is like kind of crooked there, so when you mirror it, he looks goofy there. So whatever, right? That's biology. Let's focus on the physics here there. So notice your symmetry. If it took the ball, how many seconds to get to the peak? It went up, let's see, right? 1, 2, 3 seconds to the peak. How much to come back down? 3 seconds, okay? So if you take off and return to the same level, the time up is symmetrical to the time down. You see that? So how does this help you? Here's a little trick. On problems that involve going up and down, okay, it's too much work to solve for the whole thing. Too many unknowns. You guys look tired. Let's just do half the work. So one little trick is just solve for going up or solve for coming down. And the reason why that's really nice is if you solve for just going up, then at the very peak, what can you set the final velocity equal to? You can set it equal to what? 0. That's an awesome trick because in 3 out of the 4 nifty equations, VF will just drop out because you set to 0. Is that nice? Okay. How about if you want to solve for coming down? That's also nice. In fact, that's what we're going to do today in a second, right? Because here, what can you call the initial velocity if you're solving for coming down? A big fat what? 0, exactly. Okay? So use symmetry. Here's another symmetrical pattern we can notice. What do you notice about the speeds on the way up? 30, 20, 10, 0, negative 10, negative 20, negative 30. The speeds on the way up are also what? Symmetrical to the speeds on the way down. Notice I'm saying speed, not velocity. Because on the way up, it's a positive velocity. On the way down, it's a negative velocity. But the speeds are symmetrical. So that's just kind of a nice intuitive fact to know. So if you throw a ball up at 30 meters per second, how fast will it be going when it comes back to your hands? 30 meters per second, okay? So practically speaking, it's just a symmetrical thing about gravity to appreciate. It's the same gravitational field that slows a projectile down on the way up as it is that speeds it up on the way down. So maybe a practical thing is like in the news, you hear every once in a while, like around 4th of July or some festivals, like crazy people, like in other countries, or sometimes in Texas here, but it's kind of sad. People take out their guns. Everyone's in Texas got a gun, right? And they'll shoot bullets straight up into the air. Okay, if you think about it, it's kind of dangerous, right? Or like in the cowboy and Indian movies, politically incorrect, whatever, right? If a cowboy shoots their gun right up into the air, a bullet at 100 miles an hour, why is that dangerous? Because theoretically, how fast will the bullet come back down on your head? How fast? 100 miles an hour, right? So every so often on the news, you'll hear about how like a couple people died because they were somewhere where at a festival or crazy people shooting guns in the air, right? Though in real life, air resistance would slow down the bullet. So not quite as dangerous, but still not a good idea. Okay? Finally, the last thing we can see is it's not really the distances so much, but the displacements. You can think of it that way, okay? On the way up are symmetrical to the displacements on the way down. It's not equal, but they're symmetrical about the peak. Notice that it's 25, 40, 45, 40, 25, 0. You see that? There's symmetry there. We can apply that to make our life easier. So in other words, we got a couple patterns here, okay? If it takes 1 second for the balls to go up, then how long for them to come back down? 1 second there, right? If it takes 2 seconds for the balls to go up, how long to come back down? 2 seconds, right? 3 seconds, how long to come back down? 3 seconds. You see that? So symmetry